Yes, I'm audible. Basta.
Yes.
So the last class we have finished the circuits. Now, just one second. So in class 12 syllabus, only semiconductor is left. So in semiconductor, we'll start from diodes, we'll discuss diodes, then we'll discuss circuits which involve diodes, and then we'll come to logic gates. While doing diodes, I'm assuming some theoretical topics that you have done in class 12 that you know. You know what are N-type and P-type semiconductor. Okay, what are the charge carriers in semiconductors? Upasna.
Electrons and holes.
Electrons and holes. What are N-type exactly? Yes, Upasna. What are N-type
Those are
semiconductor?
extrinsic semiconductor doped by pentavalent
Pentavalent
dopants.
impurity. Yes, they have extra electrons, right? Then holes. Then
Yes,
there are P-type.
donors.
P-type, which are doped with trivalent impurity, and they have more holes. Holes are majority charge carriers, and electrons are minority charge carriers. After P-type and N-type semiconductors, the next is PN junction. And the first device that can be made out of a PN junction is diode. So diode is just a PN junction with metallic contacts. PN junction with metallic contacts is known as diode. So if you want to draw PN junction, this will have a P type, P side. Then you have N side. In P side, you have holes in majority. These are holes. You have few electrons in minority. In N type, you have electrons in majority. Few holes in minority. And this is the depletion region, right? This region is deplete of charge carrier. This is known as depletion region. In depletion region, on N side, you have negatively charged ions. On P side, you have positively charged ions. And this is a potential which is known as barrier potential, VB. Due to this barrier potential, there is an electric field from N side to P side. This is electric field. Electric field due to barrier potential. Now, this is PN junction. If you put some metallic contacts over here, then this PN junction is a diode. This is the diode. We represent a diode in this way. This is the symbol for the P side. This is the symbol for the N side. Now, when this is one more thing, in a PN junction, there are two types of motion. What is the motion of majority charge carriers across the junction? Motion of majority charge carriers across the junction. This motion is known as diffusion. Diffusion is the motion of majority charge carriers. So diffusion will include the motion of hole from P to N and motion of electrons from N to P. This motion of majority charge carrier is known as diffusion. There is one more type of movement which is known as drift. Drift is the motion of minority charge carriers across the junction. This is holes from N to P and electrons from P to N. So when you take a PN junction, and if this PN junction is an equilibrium, means you have not attached any cell or any battery to it, then this is an equilibrium. An equilibrium, the diffusion is exactly equal to drift. If you want to use this in a circuit, then you will bias this diode. Biased means you will either support diffusion or you will support drift. If you support diffusion, then we call it forward biased. If you support drift, then we call it reverse biased. In forward biased diodes, diffusion is greater than drift. And to forward bias a diode, what we do is, this is your PN junction. This is P side, this is N types. You put P side at a higher potential and N side at a lower potential. This is forward biased. The current will flow in this direction from P to N. This is the direction of flow of current. When you forward bias a diode, then barrier potential decreases. Barrier potential decreases. The width of this depletion region also decreases. Width of depletion region decreases. This is forward biased. And your current is in milliampere. It's a large current which is in milliampere. And if you make this diode reverse biased means this is the N side. You connected P side with the negative terminal of the battery and N side with the positive terminal of the battery. In this case, the barrier potential increases. The barrier increases. So your barrier is now VB plus width of depletion region. Width of depletion region increases. In fact, not just width, but along with the width, the resistance of depletion region decreases. Width and resistance of depletion region increases. Very small current flows into the circuit, which is in microampere. Direction of current gets reversed as that of the forward bias. In forward bias, current is from P to N, but in reverse biasing, current is from N to P. Now, after this biasing, you have to draw the characteristics. In circuit theory, characteristics means V versus I graph. In current electricity, you draw the characteristics of a straight conducting wire, which is a straight line. So we draw characteristics also here. So we have two types of characteristics. One is forward characteristic. In forward characteristic, you forward bias the diode and you plot voltage versus current graph. This is the type of graph. You can see up to here, which is known as knee voltage. Knee voltage is 0.3 volt for silicon. If your diode is made up of silicon, 0.7. Although in numericals this number is given, but still for silicon, and 0.3 volt for germanium. Up to here, your graph is a curve. The variation, this is current in milliampere. So the variation in current is very small. Current increases by a small amount. But once the knee voltage is, this is a straight line, which shows current increase linearly with voltage. So what happens is here, when the diode is forward biased and your potential is the barrier potential. Potential decreases means your potential becomes VB minus V. So when your applied voltage is equal to knee voltage, that means your applied voltage is equal to barrier potential. Once they are equal, the net barrier is 0. So at this voltage, the barrier becomes 0. There is no restriction in the moment of charge carrier. The graph is a straight line. But if your applied voltage is less than knee voltage, then there is some restriction in the moment of charge carrier and graph is not a straight line. This is the forward characteristics. You can calculate two types of resistance from here, DC resistance, or you can calculate the AC resistance, which is delta V by delta I. So in forward biasing, the current is in milliampere. This is the characteristic. When you reverse biased it, in reverse biasing, both gets reversed. Like voltage, the polarity of voltage gets reversed, current gets reversed, characteristics. Initially, there's a very, very small variation of current with the voltage up to a certain voltage, which is known as breakdown voltage, or sometimes known as knee voltage. Not breakdown voltage or zener voltage. Once your applied voltage is equal to breakdown voltage or zener voltage, current increases almost linearly. Means your current increases but no change in voltage. What happens here is voltage is V is equal to IR. When your applied voltage is equal to breakdown voltage, then silicon bonds breaks. You get new charge carriers which decrease the resistance, but you are increasing the current. The product will remain constant. So at breakdown voltage, what happens? Breakdown of the semiconductor begins. Breakdown of the semiconductor means breaking up of silicon atoms into two types of ions. So you get both electrons as well as holes. So when you get new charge carriers, the resistance decreases, current increases, but the product will remain constant. That's why voltage is constant. Here also you can calculate DC resistance, which is V by I, or you can calculate AC resistance, which is delta V by delta I. Type of questions that you can get here is the two types of question. One is to discuss reverse bias, and then you have some questions on graph. Let's first one question on graph. Graphs are given. This is for a diode. This is voltage. This is current. Another is given in this way. This graph is a part of question. This is all example of NCERT. This is in milliampere. This is in volt. This is in microampere. So this is 10, this is 15, and this is 20. This is 5 volt. This is not known. And let's say this is 0. This is 1 volt and this is 1.5 volt. Here it's minus 5 volt. Here it's minus 8 volt. And this is 3. You're supposed to calculate resistance when first I is equal to 15 milliampere. Second, when I is equal to 3 microampere. Now, in this question, you will learn when to use DC resistance and when to use AC resistance. Okay, if I want to calculate resistance as at I equal to 15 milliampere. First of all, Upasana, just tell me, this is the reverse characteristic or the forward characteristic?
Forward.
Forward. So when you have to calculate resistance, when current is 15 milliampere, your current is 15 milliampere. So Upasana, do you have the value of voltage when your current is 15 milliampere?
No.
Value is not given. That means you can't calculate DC resistance. For DC resistance, you need voltage corresponding to current. So if the value is not given, that means it's asking to calculate AC resistance. For AC resistance, what we do, it's not V by I, it's change in voltage by change in current. So do one thing, you have to calculate over this point, choose 2 points, one below this, another above this. And the choose points for which you have the value of V and I. Choose those points for which you know the value of V and I. So your change in voltage is final voltage minus initial voltage. It's 1.5 minus 1. Your current is final current minus initial current. 20 minus milliampere. So this is 0.5 by 10 milliampere. 10 into 10 raised to the power minus 3. This is 10 raised to the power minus 2. So it's 0.5 into 100. It comes out to be 50 ohm. Now, Bira, what characteristic is this? Forward or reversed?
Sir, reverse.
Reversed. So you're supposed to calculate resistance. So this is your current 3 ampere. So corresponding to 3 ampere, do you know the value of voltage?
Yes, sir.
I give 2 values, just rub it up. So for 3 milliampere, your voltage is minus 5, right? So you can use that your resistance is V by I. You have voltage corresponding to current. We'll put V as 5. 3 is micro. So it's 5 by 3 into 10 ki power 6 ohm. This is how we calculate resistance. It's V by I. So it's 5 by 3 into 10 raised to the power 6 ohm. Is it clear?
Yes, sir.
Yes.
Okay, that is one type of question. For another type of question, okay, just take the screenshot and it's just theory, no formula, nothing. Just take the screenshot. But these discussions are important for objective also. What are diffusion, what is drift? Just take the screenshot. It's just theory, no need to write it. Note down this question. We'll do few more questions. Written?
Yes, sir.
Yes.
The next type of questions, you will be given a diode, just have to identify whether the diode is forward biased or it's a reverse biased. So if a diode is forward biased, then this P and this is inside, right? P should be at higher potential and N should be at lower potential. So if it is plus 10 volt and this is minus 5 volt, P at higher, N at lower, that means this is forward biased. But if P is at lower potential and N at higher potential, like this is minus 5 volt and this is plus 10 volt, then this is reverse biased. Similarly, if this is plus 2 volt and this is earthed, earthing means this is 0 volt. P at higher, N at lower, this is forward biased. Similarly here, this is minus 2 volt and let's say this is earthed. Earthing means this is 0 volt. So now P is at lower potential. See, minus 2 is less than 0. So P at lower potential at an higher potential. So this is reverse bias. So this is another type of question that you can get on diode. The next type of questions are on circuits. In regular circuits of resistors, you can get diodes. So for those circuits, the rule is if you have an ideal diode and if it is forward bias, if you have a diode and this diode is forward biased, you can replace it by a conducting wire. Now, if you have a diode, this diode is reverse biased, we call this as short circuit. Then you can replace it by an open circuit. So check the question. So you have a diode, you connect this diode with a resistor, you have another diode, you connect this diode with another resistor, then there's a cell, you connect this cell with another resistor, this is diode 1, this is diode 2, this is 5 ohm, this is 10 ohm, this is 5 ohm, this is 10 volt. You're supposed to calculate R equivalent. So first of all, you have to decide which diode is forward biased and which one is reverse biased. So in the diode 1, positive is connected to the P is connected to the positive terminal. So this diode is the forward bias and this is the reverse bias. So what we will do, we will replace the forward bias diode with a short circuit and we'll replace the reverse bias diode with an open circuit. So this is 5 ohm, this is 5 ohm, this is 10 ohm, but this 10 ohm is no more the part of the circuit, it's open. And this is 10 volt. So you can write that your R equivalent is now, it's 5 plus 5, See, you have only two resistors which are connected in series. There is no division of current here. So just 5 and 5 are in series, 10 ohm. And you can calculate current, which is V by R equivalent, which is 10 by 10, which is 1 ampere. So the current of 1 ampere is flowing. Is it clear, the circuit?
Yes.
Just note it down. Then we'll do one more type of circuit. Written?
Yes, sir.
Yeah.
Done, sir.
Okay. So another question, you have this diode. This is cell of 3 volt. This is key. This is resistance R. The key is open. It's saying that diode is of silicon. Knee voltage is 0.7 volt. And current of 20 milliampere pass through it. Calculate resistance R. So for these type of questions, what one can do is just short circuit this battery. Close the battery first. Knee voltage is given. That means voltage across the diode is 0.7 volt. So Meera, can you tell me what is the voltage across this resistor? Yes, Meera, what's the value of voltage across this resistor?
So is it 3 volt?
2.3, right? It's because total is 3 volt. Out of 3 volt, the drop of 0.7 volt is across the diode. So the remaining is 3 minus 0.7, which is 2.3, which is across the resistor. Clear?
Yes, sir.
So now you know the voltage across the resistor and you know the current passing through it. The resistor and diode both are in series. That means same current will pass through them. The current passing through the circuit is 20 milliampere. So current through the resistor is 20 milliampere, which is 20 into 10 ki power minus 3 ampere. Voltage across the resistor is 2.3 volt. So you can calculate resistance also. No? That is resistance V by I. 2.3 by 20 into 10 ki power minus 3 ohm. So this is the resistance here. So if knee voltage is given, that means this is the voltage drop across the resistor. Do it. Done? Written?
Sir.
After this, we have special purpose PN junction diodes. Special purpose PN junction diodes. In special purpose PN junction diode, the first diode is Zener diode. So in special purpose PN junction diode, we make modifications to the real diode, like this usual diode, and the modifications are done to serve a particular purpose. In Zener diode, the modification is highly doped. As compared to a normal diode, it's highly doped. Due to high doping, its Zener voltage is constant. Zener voltage is a fixed point. In a real diode, Zener voltage is not a fixed point, it can change, but for a Zener diode, Zener voltage is a fixed point. This is used as a voltage regulator. This is used as a voltage regulator. So what does voltage regulator means? First of all, we see the symbol. So as compared to a normal diode, for the Zener diode, we put a Z in. This symbol shows it's a Zener diode. If you draw the characteristic, and one more thing, it's always used in reverse bias. In forward bias, it acts like a normal diode. So whenever we use the Zener diode, we use it in reverse bias. This is the characteristic. It's a sharp point. So this characteristic shows that the voltage across the Zener diode cannot exceed Vz. Whatever the current is here, the voltage across the Zener diode is constant. Due to this, we can use it as a voltage regulator. We can use it as a device in a circuit which can maintain a constant voltage across a circuit element. So see how we use it as a voltage regulator. So say you have a resistor. Sorry. And then you connected a Zener diode here. With this Zener diode, you connected a load. In circuit theory, load means any device which is connected to your circuit. Like if you have a fan which is connected to your circuits, for you, fan is a load. If a bulb is connected, then bulb is a load. Load is any device which is connected to the circuit. And here, this is a fluctuating DC. Let's say DC is fluctuating from 0.3 volt to 10 volt. And let's say Zener voltage is 1 volt. So irrespective of this fluctuation, the voltage across the Zener diode cannot exceed 1 volt. The maximum voltage is 1 volt. So across the load, the maximum voltage is always 1 volt because load is connected in parallel to the Zener diode. Due to this feature, we say that Zener diode act as a voltage regulator. Yes, is it clear? What is voltage regulator as it exactly?
Yes.
It does not matter what is the voltage of your fluctuating supply. But one thing which remain constant is the voltage across the Zener diode. The voltage across the Zener diode will not change. So there are few questions based on Zener diode. We can take one like so the questions of Zener diode is basically the question of circuit theory, like this circuit. The circuit theory. The fact that you will be using here, this is Zener diode. So question says the current, the power across Zener diode you have to calculate. So you know one thing, that voltage across Zener diode is 10 volts. So what is the voltage across this load resistance? Upasana?
10 volt.
10 volt. This we know. Now to calculate power across the Zener diode, power is V into I. You need current passing through the Zener diode. IZ you need. If you need IZ, then you can calculate anything. You can calculate power also. This is 24 volt. This is 10 volt and this is 10 volt. So out of 24 volt, in this combination, 10 volt is going. We have discussed this thing in circuit theory also, day before yesterday, that 10 volt and 10 volt in parallel means total 10 volt. It's not 20 volt. But if they are connected in series, then 10 plus 10 is 20. But this 10, 10 is 10. So out of 24, 10 volt is the drop across these two. So the remaining 14 volt drop is across this 1 kilo ohm resistor. So you can easily calculate the current. Let's say here, this current is I. It remains I up to here. Then it divides into two parts. This is IZ. And let's call this as I1. This I breaks into two parts. One is IZ, then another is I1. You can write I1 as I minus IZ. Or let's first calculate I1 and I, and then we'll calculate IZ. So out of, for this resistor, the resistance is 1 kilo ohm. Voltage across it is 4 volts. You can calculate the current also. Current is V by R. V is 14. R is 1 kilo ohm means 1000. So I is 14 into 10 raised to the power minus 3 amp. Similarly, you can calculate I1. I1 is V by R. V is 10. R is 5 into 10 ki power 3. I1 is 2 into 10 ki power minus 3 ampere. If you have I and I1, you can calculate IZ. You can write that your IZ is I minus I1. So this is 14 into 10 to the power minus 3 minus 2 into 10 to the power minus 3. That's 12 into 10 raised to the power minus 3 ampere. Now once you have IZ, you can easily calculate power. The power is V into I. V is 10. Voltage across the Zener diode is 10 and current is this 12 into 10 ki power minus 3 amp. You have to calculate your answer in milliwatt. So this is 120 into 10 to the power minus 3 is power, that is in watt. You can remove this 10 to the power minus 3 and this is milliwatt. Yes, tell me, is it clear?
Yes, sir.
Yes.
So these are the type of questions which include both your circuit analysis that you did in current electricity and some concepts of semiconductor as well. So now note it down. Note down. Zener diode, just take the screenshot. Note down the numerical one. Yes, written.
Yes, sir. Done, sir.
No, write this question. written?
Done, sir.
Okay. Now, after this question, the next type of PN junction diode is the photodiode. Photodiode is transparent. So the modification in the diode is we make the region near the PN junction as transparent. This is also used in reverse biased. This is used to detect intensity of light. See how it works. The normal PN junction diode. This is P side, this is N side. You connected P side with the negative terminal of the battery and N side with the positive terminal. This is reverse bias. And this whole portion is transparent, so that you can incident light over it. Now let's first draw the characteristic. This is V and this is I. This is applied voltage, which is always less than the Zener voltage. We always kept this applied voltage less than the Zener voltage. So when you don't I characteristic, since your voltage is less than the Zener voltage, so this portion of the graph is not possible. Huh? This is it. Since there is no light, we call this as dark current. Dark current means you don't incident any photons yet. But when you start bombarding it with the photons, when you incident photons, on energy of photon is h nu, which is greater than the band gap. You incident only those photons which have energy greater than the band gap. So in this case, what happens is new electron hole pairs are generated. Due to new electrons hole pairs, the current increases. This I1 is intensity. Current increases. When you increase the intensity further, means you are incidenting more electrons and protons, your current will increase also. So on increasing the intensity, I2 greater than I1, on increasing the intensity, your current will increase. So just by looking at the current, you can decide what is happening with the intensity of the light. So when you did not incident any photon, then the current is dark current. But when you incident photons and you keep on increasing the intensity of photon, current also increases. That's the photodiode. In numericals of photodiodes, you can't get any circuit. You can just get the numerical of this thing. Planck's quantum theory. You know that E is equal to h nu. Band gap is given, and it will ask you to calculate the frequency of light or the wavelength of the light. That's it. Otherwise, you will get conceptual questions based on this V versus I graph. That which intensity is higher, which one is dark current, all those things. Take the screenshot. After photodiode, there are two more special purpose diodes. One is LED and another is solar cell. There is nothing in LED or solar cell on which numerical can come. So you will do it from NCERT. You just have to remember the graph. Then for LED, you have to remember the material use, material and the band gap to make green LED, to make red LED, to make blue LED, to make ultraviolet LED. You have to measure what is the band gap and what is the material used. Solar cell, just the V versus I characteristic. Again, you just have to memorize it, nothing else. So you won't get any numerical on these two topics. But yes, on photodiode, you can get one numerical, which is this h nu is greater than or equal to band gap. So you're supposed to calculate frequency and wavelength of the radiation. And the symbol of photodiode is this. Just draw this symbol, please. When you circle over the diode, that means it's transparent, and this is photons. Photons are incident on the diode. For LED, you will memorize the material used and the band gap and the solar cell. Okay, after this, the next is logic gate. We have three types of gates. One is OR gate, another is NOT gate, third one is AND gate. Logic gates, do you have computer science with in class 12?
No, sir.
No, sir.
So logic gates are basically electronic circuits which can perform logical operations. Logical operations like addition, subtraction, multiplication, means these are the basic building blocks of the logic that a computer use. This is mostly the part of computer science syllabus. So for us, logic gates are like set theory. The set theory that you did in maths. Do you have Boolean algebra in mathematics? Yes. Is Boolean algebra also a part of syllabus? Maths, in maths, do you have Boolean algebra or not? Yes, no, Mira, Upasana. You have Boolean algebra in your maths syllabus or not? Class 12 syllabus.
No, sir.
Okay. So consider this logic gate as sets. So you have three types of gates: OR, NOT, and AND. OR gate, the operation on which the OR gate is based is union in set. The NOT gate is based on the logic of complement in set theory. AND gate is based on the logic of intersection. Let's start with the OR gate first. First, we'll see the symbol of the OR gate. So this is the symbol of the OR gate. OR gate have two inputs, A and B, and there is one output A. The Boolean is A or B. So if you want to build a OR gate, let's first write the Boolean algebra, then it will be easier. So Boolean algebra is this symbol is the symbol of OR gate. This is OR. This is the algebra that we're using here. And how to use this algebra? To use this algebra, we have to make a truth table. So you have one input A, you have another input A, and you have output. These are two inputs. And this is the output. So you have two inputs and one output. In digital electronics, this gate is a part of digital electronics. You have only two types of signals, which is either 0 or 1. We don't have any other decimal like 2, 3, 4. These numbers are not there. In digital, you have only two types of numbers, 0 or 1. It's binary basically. 0 by 0 means that switch is off. By 1, it means switch is on. So if you have both 0, then Y will be 0. In OR gate 0, 0 will be 0. In OR gate 0, 1, 1 is 1. In OR gate 1, 0 is 1. In OR gate 1, 1 is 1. If any of the input is high, then you will get the output. Then you have to do it using the waveform also. First, we will draw the waveform for the first input. So the waveform is, if it is 0, 0, 1, 1, this is 0, this is 0, this is 1, and this is 1. Then you have 0, 1, 0, 1. This is 0, this is 1, this is 0, this is 1. Then we have 0, 1, 1, 1. This is 0. Then we have 1, we have 1, we have 1. This is 0, 1, 1, 1. This is the waveform. So for every gate, you should know the symbol of the gate. You should know the Boolean algebra. You should know the truth table, means for a different combination of inputs, what is the output. Then you should know how to represent this truth table in terms of waveform. This is known as waveform. Yes, is this clear? Because this was not in class 12 syllabus, something new.
Yes, sir.
Yes, sir.
This is an NCERT, but it's deleted for the last 4 years. It's a part of deleted syllabus. Okay, just note it down. Note down. Don't take the screenshot. This is important. Tell me once you have written.
Done, sir. Yes, written.
Yes, sir.
Okay. After OR gate, we have NOT gate. Achha, there is one more thing that we can do is we can draw the analog circuit also for it. Analog circuit means using bulb and cell, we can make a circuit which looks like this, which follow this logic. That if one of the switch is on, then your bulb will glow. So this is the cell. This is the bulb. And you connected two switches here. Both the switch are open. If both the key is open, what does it mean? If both the keys are open, it's 1 1 or 0 0.
0, 0.
0 means off, right? Bulb will glow, it will not glow.
Will not.
It will not glow. That means 0 0, it's 0 also. But if I close one of the key, what will happen? Now the circuit is closed or not? Circuit is complete or not?
It's complete.
It's complete. So bulb will glow. So when you give 1, 0, it will give 1. If you close this one and you open this one, then also your bulb will glow, it's 1. But if you close both, then also your bulb will glow, 1, 1, 1. So this truth table can be explained through this analog circuit. Draw the analog circuit also. We'll do NOT gate then. NOT gate have one input and one output. This is the Boolean algebra. This is the complement of the set. So if I draw the truth table, this is A and this is Y. If I take 0, the complement of 0 is 1. If I take 1, then the complement of 1 is 0. The next is waveform. Now drawing waveform, you know how to draw the waveform. The next is the analog circuit for it. If you take this cell, you take this key and you connect this. This key is open. This bulb circuit is complete or it's broken somewhere. Key is open. Circuit is complete, right? Current can flow from here. So bulb will glow. This is 0. Bulb will glow. This is 1. But when you close the circuit, this cell gets short circuit. Short circuit means there is no current that will go to this bulb. The current will go here, then it will come here, then it will come here, then it will come here. It will not go into the bulb because current always follow the short resistance part. When the current comes here, it have two paths. One path where there is conducting wire having 0 resistance. In the another part, you have bulb which have a high resistance. So current will not go into the bulb. It will follow the low resistance path. Is it clear?
Yes, sir.
So that's NOT gate. After NOT gate, the third type of gate is AND gate. AND gate is like intersections. Again, have two inputs, not have one input, and have two inputs and one output. This is A and B. So if I write the truth table, this is A. This is the operation, A and B. B and Y. So this says 0, 0 is 0. 0, 1 is 0. 1, 0 is again 0. It's just 1, 1 which will give 1. Draw it, then I will draw the analog circuit of it. Yes.
Done.
Sure. After AND gate, you can draw the analog here also. This is cell. This is one key. This is another key. And this is the bulb. The keys are open. If both the keys are open, then no current will flow into the circuit. The bulb will not glow. If I close one key, the circuit is complete or still incomplete?
Income.
Still incomplete, right? This is closed means this is 1 and this is 0. Still is incomplete from here. Current will not flow, bulb will not glow, it's 0. But when you close both the keys, then bulb will glow and then you will get 1. So this is the analog circuit for the AND gate. Just note it down. Then we do combination of gates. Yes, written?
Yes, sir.
Okay. After this, we have combination of gates. We can combine these gates to make various gates. These two combinations are important. One is NOR gate, another is the NAND gate, another is the XOR gate. NOR, NAND, and XOR gate. Let's first discuss. XOR is not a part of syllabus now, so we'll just concentrate on NOR and NAND. It's not even in JEE main syllabus. So the NOR gate says you take an OR gate, two inputs. This is output Y1 of the OR gate, which is A or B. At the output of the OR gate, you put a NOT gate. So your Y is A or B bar, which is Y1 bar. This is your NOR gate. You can draw a shorthand symbol also. This is A, this is B. You can put this bubble here. This bubble will represent the entire NOT gate, and you will get Y, which is A or B by. This is shortcut notation. So if I write the truth table, this is A, this is B, this is Y1, which is A or B, and this is Y, which is Y1 bar, which is A or B bar. So if I take 0, 0, 0, 0 is 0, but you take complement, it's 1. 0, 1, it's 1, but if you take complement, it's 0. 1, 0, 1, if you take complement, it's 0. 1, 1, 1, but if you take complement, it's 0. So this is the truth table of the NOR gate. So this is the Boolean algebra of NOR gate. After NOR gate, the next gate is the NAND gate. In NAND gate, it's AND gate. This is input A. This is input B. This is the output of the AND gate, which is A and B. At the output of the AND gate, you have a NOT gate. So this is Y, which is Y1 bar, which is A and B bar. So this is A, this is B. This is Y1, which is A and B. This is Y, which is A and B bar, which is Y1 bar. So if I write the truth table, 0, 0 is 0, the complement is 1. 0, 1 is 0 in AND gate, but the complement is 1. 1, 0 is 0 in AND gate, but the complement is 1. 1, 1 is 1, and the complement is 0. This is the truth table for the NAND gate. And you can draw the shorthand notation also. This is A, this is B, and this bubble will represent the NOT gate, which is A dot B bar. Note it down.
Done, sir.
Okay. Tell me once you have written.
Done, sir.
Okay.
Done.
Okay. Now let's do some questions over this concept. First type of question is obtain. And just one more thing, note it down that this NOR gate and NAND gates are also known as universal gates. They are also known as universal gates. They are also known as universal gates. The reason is if you have NOR gate, then you can obtain all type of gates. If you have NAND, you can obtain all types of gates. That is the question. Obtain all gates from NOR. So first thing is let's obtain not from NOR. So for this, we'll first use Boolean algebra. So for the NOR gate, the Boolean is this, it's A or B bar. If I put A is equal to B, means both the inputs are same, then I can write this as A or A bar. In set theory, A or A is, this was NOR and this is NOT. So to go from NOR to NOT, this is the key, A is equal to B. You can draw it here also, just make both the inputs same. Sorry. This is NOR gate or NAND gate, this symbol. This is a symbol of NOR gate or NAND gate? NAND, right?
Nor.
This is NOR. Huh? In NOR, the first one is bit. So this is NOR. So if I connect both the inputs, that means if I give A here, then A will come here. Now it's not NOR, this is not now. Because if A is equal to B, then this NOR will convert to NOT gate. So that's very important. Anywhere in the question, if you get a NOR gate, this is a NOR gate, right? This is a NOR gate. This is NOR. But if you join those both the inputs, then it becomes NOT. Second is it will ask you to produce AND, not AND, NOR from NOR. It will ask you to produce OR gate from NOR gate. So to produce OR from NOR, what we can do is see why is A or B bar. This is NOR gate. But if I take one more complement, then complement of a complement is cancelled out and this is A or B. So this is NOR gate. Putting one more complements means putting NOT gate over it. So if you take a NOR gate, this is NOR, right? This is A, this is B. So this is NOR gate, this is Y, which is A or B bar. If I pass it through a NOT gate, but that NOT should also be obtained from the NOR gate. This is the NOT gate. This is the NOR gate. So output here is A or B ka complement, which is A or B only. So this whole thing is your OR gate. Yeah, this is clear.
Yes, sir.
Similarly, the third question is, can ask you to produce AND gate from NOR gate. Here we use De Morgan's theorem, which says if A bar or B bar, if we take whole bar, then it comes out to be A dot B. In set theory, we call this as De Morgan's theorem. So if you take, you need A bar. A bar means you take a NOT gate and that is obtained from NOR. To obtain NOT from NOR, we connect both the inputs. So this is Y1, which is A bar. Similarly here, this is B. This is Y2, which is B bar. You connect it to a NOR gate. So here, the one input is A bar, another input is B bar. So you have A bar or B bar, whole bar, because this is NOR. So you get A and B. This whole gate, this whole up to here, if you combine everything, this is the AND gate. Is it clear?
Yes, sir.
You can get the same question, but in opposite sense. Like it can ask you to produce all these gates using the NAND gate. I'm sharing that question also. Just note it down first.
Done.
Sure. Written?
Yes.
Yes, sir.
Okay. So from the operations team, you must have got 3 screenshots, right?
Yes,
Received?
sir.
Okay, so that is all three gates from NAND gate, the same procedure. These two are important questions. We'll do one more question from the PYQ. Let's do this question. Do it. See, to solve these type of questions, now first of all, algebra for y. So how to proceed? This is which gate is this, Upasana? And so one input is A, another input is B. So this is your output, which is A and B. This gate? Not. So the input is B,
Not.
so the output is B bar. Which gate is this?
Or.
OR gate. So one input is A dot B, another input is B bar. So this is A dot B or B bar. If you want to write the newspaper, first write A, then write B, then write A dot, then write B bar, then write Y, which is A dot B, B bar. So A and B 0, 0, A dot B is 0, B bar is 1, Y is this or this, 0 or 1 is 1. Then you have 0, 1, 0, 1 is 0, B bar is 0, 0 or 0 is 0. 1, 0, A dot B is 0, B bar 0, bar is 1, 1, 0 is 1. 1, 1, 1 dot 1, 0, 1 or 0. So which is the answer? This one. Yeah?
Yes, sir.
First write it will not take more than 30-45 minutes. Related questions from PY. Gate and modern physics both are very scoring. Last 2-3 attempts, 3 questions with this modern physics and semiconductors. So 3 questions are set then. Yes, is it clear? Written?
Yes, sir.
Okay. So that was the last topic. So I'll stop here. Tomorrow, one of you have exam. Upasana, you have exam tomorrow? So best of luck for exams, both of you. And
Thank you, sir.
advice, please don't do any guess work in the exam. Try to minimize the negative marking. But it's very, very tough, and you're able to solve just 15 questions, including all 3 subjects. Then just attempt 15 questions only. That will give 100%. If paper is tough, it's tough for everyone. The the score versus percentile will go down. If the paper is easy, maybe for 120 marks, someone is getting 95 percentile. If paper is very tough, then maybe it goes to 90 marks or 95 percentile. Don't do any guesswork there. Just touch only those questions on which you are very confident. Negative marking is very, very dangerous. And try to revise once all relations that you have done in the last 2-3 weeks. Okay.
Yes, sir.
Okay. So let's stop here. Thank you. Bye. Good luck.